I hope you can hear me also online. Again, thank you very much for the kind invitation. I'm really happy to be here in a different context, not the university context, but in industry. It's also always nice to get a different perspective on things. And I was quite surprised that you have this really nice office building and large company here. All right, what I want to talk to you today about the navigation of chemicals with cost spectrum methods, these supervisor have developed. And since we are an interdisciplinary audience here, I thought it makes sense to start with a bit longer introduction and clarify some terminology. In particular, what is chemical space? This is quite an esoteric term if you have never heard it before. And informally, you can assume that chemical space is the entirety of all existing molecules. A number that you will find in literature is 10 to the power of 60 different molecules. This is a combinatorial estimate from this guy you see on the lower left, John Louis Raymond, who is the chair of chemoinformatics in Bern. And he arrived at this estimate by thinking, okay, we have different atom types that can be connected to each other via chemical bonds. And if you iterate through it, so a carbon atom can be bound to 4 different atoms, a hydrogen bond can be bound to 1 atom, then you arrive for molecules up to a certain size, so this number doesn't even contain everything, you arrive at this estimate. And he is already doing something here that is the critical thing in coming up with a definition of chemical space. He is assuming a representation, namely a representation of a molecule as a graph. So the atoms are the nodes that are connected by the chemical bonds as the vertices. And yeah, and herein already lies the big problem, because you don't have a unique metric or topology or a representation of your molecule, which is also why databases, as you can see here on the right, I hope you can see my cursor online, they differ quite widely in how many molecules are stored. So the 2 largest databases that we have got are the PubChem, which contains around 150 million different molecules, and the CAS registry, which contains around 280 million molecules, which both is far off from this number on the top left. So yeah, you can also think about this as a technological limit. If you would be able to store a single molecule as 1 byte, this would still be something like 10 to the power of 39 petabyte or something. And for comparison, the internet is 120 or so petabyte, or yeah. So there's orders of magnitude difference in what can a database store and what would be combinatorially possible. Logically, many smaller databases that are used in the field, for example, the chemical databases, are even smaller than these 2 databases. So the Campbell, which is popular in chemoinformatics, you can see here, has around 3 million compounds. So I'm summarizing, the chemical space is unfortunately representation dependent and therefore ill-defined. For us working in theoretical chemistry, it is now a task to come up with a more confined definition of chemical space, something that we can handle, in fact. And relevance or confinement is the right keyword here, because we can define chemical relevance via the potential energy surface, for the energy of a molecule that we can compute. Simply said, we have the representation that we are choosing of atoms in Cartesian space. So we are providing a set of atomic coordinates as Cartesian coordinates. And each molecular structure that we can come up with here would correspond to a minimum on a potential energy surface that we can compute with this input. The relevant regions on this potential energy surface are therefore the local minima on such an energy surface. We have different energy basins, so collections of different minima, collections of stable structures. And sometimes, depending on what you are asking for, you also are looking at transition state regions, so saddle points on the potential energy surface. Furthermore, the shape around the minima on the potential energy surface helps define us the molecular thermodynamics of a molecule. So the accessibility, not just the existence. The important thing about this representation is that most of chemical space, as I tried to define it on the previous slide, is high in energy and therefore irrelevant for us. So we don't need to treat it, don't need to look at it really. I just threw in the energy of a molecule as a further term. And if you are not coming from a physical sciences context, this might be esoteric for you as well. But it is really what you're always doing in physics. You have different particles interacting with each other and can define a potential or an energy depending on this interaction. And for chemistry, we are mostly moving here on the left side. So if you are looking at classical mechanics, you have the atom-atom interactions. If you go to quantum mechanics, you have additionally the interactions of electrons in the field of nuclear coordinates. So still the nuclear coordinates are your basic input, but you're looking at the electrons. Why is the energy important for us? Why are we as chemists interested in the energy, aside from trying to define chemical space? Well, as I already teased, we have different stabilities. We have look at transitions on the energy surface, so going from one minimum to another via a transition state. This is exactly what defines chemical reactivity. You can relate these energy barriers even to reaction constants. You can look at energy differences also between different electronic states. So a figure that the Droyf group in Heidelberg likes to use is this one for energy storage systems, photochemical energy storage systems, where you excite a molecule from a ground state into excited state by shining light on it, from where this molecule can then relax and you can do some chemistry, further chemistry with it. You also can derive particle movement via derivatives of the energy and normal modes via the second derivatives of the energy with regards to the nuclear coordinates. Which are going into the thermochemistry of the system, so help define the accessibility. More generally, however, you also can derive different properties from the energy as different derivatives. So this is kind of the attempt on a general formula for properties derived from the energy. So you have different partial derivatives of the energy, for example, with regards to internal and external magnetic and electric fields and moments of the molecule or the coordinates. Looking on the left, this table gives you some examples for these partial derivatives. If you look, for example, in that line right here, the partial derivative with regards to an external magnetic field and internal magnetic moment gives you the nuclear magnetic shielding constant, so the NMR constant. Right. The general thing that we can say here is that property predictions are how we relate the Hamiltonian, the energy function, the wave function, to the energy as an expectation value of our input, the nuclear coordinates. And this closes the cycle back to the chemical space, because this last part, the green part here, the sentence, is why we have to investigate chemical space. Giving you a simple example from a property, what you see here is two simulations of an IR spectrum with a cheap quantum mechanical method for the same molecules, two different members of the chemical space of the same molecule. So if you ask an organic chemist, he would draw you the same molecule for both forms. But they are clearly not the same, and they give different properties depending on what you're calculating here. Right. What other parts of the chemical space are important? So what I just showed you is the first thing here. So same connectivity of the molecule, different spatial orientation. This is called a conformation. You also have different states of the molecule. Because I can't plot it here, I show a protonation state, but this is also representative of different electronic states. You have different isomerisms, so different connectivities for the same amount of atoms, for the same types of atoms. And you have a special case for intermolecular interactions. So this is a special case of the molecular conformation. You have different interaction motifs between molecules that are not directly connected to each other. Right, so what's left to talk about is methods that we use to describe these things, methods to derive an energy of a molecule. And historically, there have been different philosophies in trying to come up with what is a good method to describe an energy of a molecule. So this started out with trying to understand what is chemical bonding, going to the 100-year anniversary this year, Schrödinger's equation, to density functional theory, so still the workhorse of quantum chemistry, to some more approximative methods like QMMM and chemoinformatics, with kind of an open end where we are right now. And again, historically, there have been different philosophies. One person that tried to come up with terminology of this is Charles Colson, who described the two philosophies as a posteriorists, so chemists that are more concerned with deriving correct chemical trends for a system, versus the a perniciouists, who he defined as people that are concerned with finding a good or the best approximation to the Schrödinger equation. And one quote that he made at a conference in the early days of DFT is, "Give us insight, not numbers," which at that time he made as a pro-DFT argument. So an argument in favor of providing chemical insight into a system instead of number crunching, so really expensive calculations. Funnily enough, you could read the same quote the other way around, that only the correct physics gives us the correct insight and everything else is guesswork and just numbers. So maybe not the best quote to make here. Anyways, what came into existence from this were different types of theories that are often correlated in accuracy and computational costs. So more accurate methods are typically more computationally expensive and include less approximations, which also leads to a relation to what kind of system sizes you can describe depending on the method. So yeah, at the lower end is the high accuracy method. These are all kinds of wave function theory. So for example, the ADC code of the Rolf group would be classified here. DFT can describe some larger systems. If you discard the quantum mechanical picture, so the electronic picture as a whole, you end up with interatomic force fields, which allow you to describe really large systems. Going even further beyond that, discarding even more physics, you arrive at some point at QSA and AI machine learning models. And right here in the middle between DFT and force field methods, we have basically chemoinformatics. Structure-activity relationship, quantitative structure-activity relationship. In the middle here, you have SQM, which are the low-cost electronic structure methods from my talk title. And the approach here is kind of that you try to find the best of both worlds, maybe also the worst of both worlds. These are not exclusive. So you are still looking at an electronic structure picture in some sense. You have a Hamiltonian which you parameterize heavily like you would in a force field method. The goal here is still to find the approximate solution to the Schrödinger equation, a really approximate one here. And due to the parameterization, reduce the computational scaling so that you can have a quantum mechanical calculation for larger systems. The methods I'm in particular referring to here are the extended tight binding methods, which were developed in my former group, so by Stefan Grimme. These are an approximation to DFT. What you see here is a generalized DFT formula equation for a non-local DFT method. which you are approximating with a Taylor expansion. You are parameterizing this method with atomic parameters to basically the whole periodic table, have some additional classical terms, but still in the end you are trying to derive a electronic structure. Methods that are used here and that I'm referring to in the following without explicitly going into detail are the GFN XTB methods. So these three were, a good review is by Christoph Conrad here, and more recently the next generation XTB method is the GXTB, where the G stands for general. You can see here the preprint was just published last year. Yeah, a quick word on how the computational cost actually relates to these methods. What you see here is a relative scale of computation times of different quantum mechanical methods. The reference point you see here in red, this is B3lib 631G star, chosen not because it's particularly good, but because it's the most cited method combination in literature. So this is our reference point here, 1. On the right side, you have larger basis, DFT and wave function theory methods, which routinely cross over this dotted threshold of chemical accuracy here. So you want to be better than that, ideally. On the left side, you have more approximative methods, so small basis DFT methods and composite DFT methods. On the very low end, you have force field methods that get really cheap, so 3 orders of magnitude cheaper than this DFT method. And in between here, the tight binding methods. I also plotted in here machine learning interatomic potentials, which is a bit more fuzzy, so you can get really good with them if you train them to a specific purpose, but in general, it's quite fuzzy trying to place them in this figure here. And one further thing I plotted into here, the low energy chemical space exploration. So you want to use methods at this end right here due to cheap computation costs to do these kinds of exploration. Right, with that, my lengthy introduction is done. I hope you found that insightful. And what I want to do now is move on to actual research I'm currently doing in my group, my really tiny group. So I have 1 PhD student right now. And when I try to place my research, I'm usually referring to these 5 points here, which I am summarizing into 3 sections I am talking about now. The first one is open source software development and the chemical space exploration itself. And what I've been working on for most of my career and still continuing to do so is working on an open source program for chemical space exploration called CREST. This originated from the conformational sampling aspect, so one particular part of the low energy space. We also have some tools to generate explicit solvent clusters, different protonation states. We are building out the thermodynamic parts at the moment. We're trying to calculate entropy and so on, and we have some special calculators for minimum energy crossing points, for example, and some QMM. Yeah, but as you can see here, the red part is still the focus of this program, and this is what I will address now in the following with the global optimization problem. The global optimization problem is essentially what you're trying to solve with conformational sampling. This is opposed to local optimization, where you are trying to find the closest minimum to your starting point. So if you are picking some structure from a database, it is in some geometry, so you have a set of coordinates. You want to find the minimum to do property predictions, and a typical geometry optimization leads from the starting points, these are the green points, to the closest minimum. The global optimization is contrary to that, that regardless of your starting point, you're trying to end up in the same minimum and ideally the deepest one or the few deepest ones on the potential energy surface, because this is what nature does in the end. So nature doesn't compute potential energy surfaces, of course, but it goes downhill, so to say, to a favorable state of the molecule, which, if we have a good potential energy surface, should correspond to these global minima. Right. The same kind of problem is relevant in different contexts. So the conformational sampling is certainly the prime example of this. Similar things are expected in crystal structure prediction, or also in the fitting of a potential of a force field or a machine learning interatomic potential. This is essentially the same thing. For our example, the one I showed earlier, the global minimum here would be that one on the left. So the red spectrum would be what is closer to the experiment in the end. Of course, it's not really that close to the experiment at a cheap level of theory, but the global minimum is what you would observe. Which I guess makes sense because you have here this interaction between the switch ionic parts of the molecule. So an interaction at that point is quite favorable. Right. The big challenge for global optimization is that we have a lot of different minima that we might end up in, and our energy function, our energy evaluation itself is quite expensive. So a typical DFT method scales cubically with the input parameters. And on top of that, you have to consider how many of these energy evaluations you have to do, even for local optimization. For chemical systems, we can quite nicely estimate them, at least for organic molecules. The number of minima on our potential energy surface is proportional to n to the power 3 to the power of small n, where small n would be a carbon-carbon sp3 bond. So you have 3 different orientations of a carbon bond that can up in. And usually you need for one local optimization 3 large n optimization steps on average to end up from your starting point in a local minimum. So if you combine these 2 numbers, you would need energy evaluations in the millions, even for small molecules. And you can't really avoid that. You have to do this if you want to perform a global optimization. So if you have this many points that you need to explore, your only option, if you want to do it in a finite time, is to go to cheap potentials like a force field or a semi-empirical method. Which opens up the questions, are these methods good enough for this purpose? What I'm showing here is a weighted error measure over different sets of conformational energies, so calculated with a high-level method as a reference, that you can see up here, versus the relative energies you get out with different other methods. In dark blue, you have different force fields, so no electronic picture here. In light blue, you have different tight binding methods. Dark red are semi-empirical methods derived from Hartree-Fock. And on the right side, you have different DFT methods. And you can already see you have a large difference between these methods, and could be tempted to say, okay, even if we have to use cheap methods in order to cope with a high amount of calculations, our errors are quite large. Does it then make sense to use these methods? What you see on the right is a different representation. So these are some of the benchmark sets summarized in this weighted error measure for different methods. Again, the smaller the area is, the better the method in this picture. Basically, you see the same thing for these 2 representations. And the thing that really saves us here is that we still have okayish correlation between the different methods. So ideally, it would look something like this. So this is a quite good DFT method versus the reference method. And on the lower end, you have the GFNFF force field and the GFN2XTB SQM method, where at least the GFN2XTB method, okay, it has a high error, but the correlation is still good. And what you are seeing here mostly, or most of the time, is that your energy surface is a bit compressed compared to the reference surface. You see it on the side. We have the same mass in a small energy when compared to higher level mass. However, the energetic ordering of different conformers is still more or less the same. So a good molecular structure on a cheap potential energy surface is still a good good structure on with a higher level method. For example, for this peptide here, the better conformations that you see here are always the folded ones versus the linear ones. Right. Aside from the energy, then we have to address how to actually move along the energy surface, how to find new minima here. And what we were pursuing, we are pursuing, is a physically motivated approach. So we are letting the system evolve according to Newton's equation. This is called a molecular dynamics simulation, which we additionally modify by a penalty function, V bias here, that at given times during the simulation adds a penalty on already explored regions of the energy surface. What this means is, over time, we are filling up basins on the energy surface with these penalties, and the simulation will automatically explore new regions on the surface until we have it ideally all filled up with these penalties, and therefore explore the energy surface completely. To give you a visual example, on the right side, you see two simulations that are deterministic, so identical settings, except that for the lower one, for the blue one, here online it's a bit slow, apparently, we have this penalty function, and without the stuttering, you would see that the blue simulation explores more conformations, more floppiness of the system in the same simulation time. So qualitatively, this approach works quite nicely. Effectively, what it does in the simulation is heat it up. So every time we are adding a penalty function, the simulation heats up, but quite quickly relaxes again. So this is good behavior. There are, of course, alternative approaches. I'm including one example here, the basin hopping approach, which is a Monte Carlo-based procedure. So you are adding a random perturbation to your starting point, perform a local optimization, and accept or reject this new minimum or the same minimum that you end up in with the local optimization based on a probability threshold as in typical Monte Carlo simulations. I'm including that because other program that has become popular is the GOAT algorithm in Orca. So this is what GOAT does in principle. Benchmarking these different algorithms against each other is non-trivial. It really depends on what you're looking at. On average, all of these algorithms perform similar. I would say you are finding good regions of the energy surface regardless of this algorithm. What both or all of these algorithms suffer from, however, is redundant structures. So you can have a degenerate minima on your potential energy surface that are founded or derived from the chemistries that we are looking at. And we are distinguishing from conformers, the so-called rotamers, that are the degenerate conformers. So one minimum can have many rotamers that are the degeneracies. The typical example here is the methyl group rotation. So I've numbered the hydrogen atoms here. It's still the same molecule, both give the same energy, but formally the system, the coordinates that the computer looks at are different. And we, of course, want to find out where are these different systems, what measure can we use to distinguish these different structures. It makes sense to go to a Cartesian RMSD measure as the first address, so to say, so trying to align different structures to minimize this measure based on a rotation and shift. However, this would still exclude these rotamers. You are not solving the permutation issue. with this approach. So two different conformers give a large RMSD, but two different rotamers, despite being the same minimum on the potential energy surface, also give a high RMSD. You have different options to resolve this permutation issue. One would be brute force matching, which you really don't want to do. It scales n faculty. A better alternative is using something like a Hungarian algorithm. So depending on the implementation, it scales cubically. This is basically the better implementation. However, this also has some additional problems. You still have to do the alignment when you want to use the assignment algorithm. Ideally, you need to do it before you are running the Hungarian algorithm, and therefore it is unfortunately unusable for large ensembles. Plus, even then, you can have some additional issue because there are special types of these rotamers, which you could call false enantiomers. So these are permutation and inversion isomers of the same system. I'll give you an example. So this is pentane, 4 different pentane rotamers. I've color-coded the terminal carbon atoms. You can interconvert 1 and 2 into each other by rotating in the plane of the molecule. You can likewise interconvert 3 and 4, but you can't interconvert 1 and 3 or 2 and 3 and so on, because this needs a mirror operation. All of these still are rotamers. They are giving the same observables. On the left, you're seeing IR spectra. These are identical. They also give you the same NMR parameters if you calculate them. But you need to fix the assignment. So you get the same chemical shifts and shieldings depending on a hand assignment of the different hydrogen atoms. For the RMSD, what you're seeing is if you compare these, you only get a 0 at the diagonal. What you really want is an RMSD measure that explicitly includes the permutation and the inversion and gives a 0 across the board for all different rotamers. So this tells you, okay, we really have the same minimum. What I came up with is an improvement to the RMSD algorithm. I'm calling it invariant RMSD. So we have the rotation matrix U still in there and a permutation matrix P, which you are deriving from a Hungarian algorithm. And you are trying to accelerate this Hungarian algorithm by a divide and conquer approach. So you're solving on a cost matrix. This is a distance matrix between the two molecules you want to align, and modified by only comparing those atoms to each other, so building sub-matrices that can be similar in the first place. The easiest implementation would be only comparing the same atom types. You can push it further by going to something like a canonical Smiles-like algorithm, which assigns a atom identity for each atom. For caffeine, as you see here on the right, I've plotted these identities, which are for the heavy atoms all unique. So you don't have to solve the Hungarian algorithm for these atoms in any case. Only the hydrogen atoms would have degenerate identities. So each methyl group would have 3 different IDs. And for this molecule, therefore, you would have 3 sub-matrices that you need to solve with the Hungarian algorithm, which is much, much cheaper than trying to solve the whole thing and less error prone. This is an open source pip package. So if you want to try it, and Tobias Kasun from the Droif group, we published this just before Christmas as an open source code. So feel free to try that out. You could also think about reusing these degeneracies from that algorithm for assigning NMR equivalencies directly without trying to sample the whole rotamer space. Okay, yeah, this is just about the performance. So we tested this by taking one conformer for different structures, making 100 copies of that and randomizing the entire atom order. So you wouldn't be able to align it with an RMSD, but with its RMSD, you end up in the middle, so RMSD of 0, while the blue part is the reference, the better reference point here. This is the standard RMSD, which varies around the typical average atom-to-atom distance in these molecules if you randomize them. I think this makes sense as well. Right, if you throw this algorithm at conformational ensembles, what you then see and what you want to see is especially these lines right here, so these horizontal lines of points, which tell you there are several rotamers in a conformational ensemble that you sort out because they are equivalent anyways, right? So you're finding out we have several structures that by IRMSD correspond to the same structure anyways. Okay, with that, all right. I'd like to move on to thermochemistry. And a short recap. So aside from the energy that you calculate, if you want to assess molecular thermodynamics, you need to look at the partition functions. You have several different ones. You have the electronic one, you have one for translation, rotation, and molecular vibrations, for which the conformational part can be treated separately, approximately separately from the harmonic frequencies. And what you can calculate from the energy explicitly or from the potential energy surface is the partition function for the molecular vibrations. A short recap here on the left side. So this is, again, the partition function. We need as an input the frequency, so the vibrations of the molecule. These you get from the mass-weighted force matrix, F, in which the molecular Hesse matrix is included, and the Hesse matrix is simply the second derivatives of the energy with regards to the molecular coordinates. So by diagonalizing the system, you are getting the frequencies as eigenvalues and can plug them into the partition function. Unfortunately, you can imagine that setting up this Hesse matrix can be quite expensive. If you want to do it numerically, you have to move each atom once plus, once minus, and trying to get the finite differences from this. So in the end, you are trying to do 6n calculations, where each of these evaluations at DFT cost is, again, cubically scaling with the system size. And logically, you don't want to do that for systems like these, right? So these are really gigantic. Even doing one DFT single point for these will be expensive. Doing a Hessian and an optimization before that is nearly impossible on a standard computer. So how can we go on about and try to make this cheaper? So one thing you can try thinking about is, especially for these non-covalent systems, again, deploy a divide and conquer approach where you only include as a starting guess for your Hessian the Hessians for each individual fragment. So computing them numerically is much cheaper than for the whole system. What we is my PhD student Lucas and I are currently working on is trying to derive that automatically from the optimization, the local optimization that we are needing to perform anyways. Local optimization, we have different kinds of algorithms. All of these are Newton-Raphson based, so you are doing your coordinate step between different steps based on a Hesse matrix itself. And of course, the Hesse matrix is itself what we need for the partition function of frequencies. So our idea is, can we simply reuse that Hessian from the geometry optimization to get the frequencies and therefore free energy contributions from the partition function? Standard algorithm would look like this. You are choosing a starting matrix, as you do in a local optimization as well. So this can be a scaled identity matrix. This can be a force field. So if you're performing a DFT optimization, this can be a cheaper matrix, like from a force field, or it can be this fragmented Hessian from the slide before. You're running your optimization with different iteration steps, and at the same time, this is the blue part, are logging the delta R, so the coordinate steps and the gradients, which you can then plug in this recursive formula that's used in the geometry optimization as well to construct a Hessian that you then use for free energies or the vibrational partition function. This is quite a new figure, so this is basically from Friday last week. And it seems to work to some degree. So even with cheap matrices, we are getting, you will probably not seeing that completely on this small figure, around 5 millihartry compared to the exact Hessian, which is bad in a chemical sense, but okay for ranking relative free energies in a conformational ensemble, considering that we get this information for free, basically, from the local optimization. On the right side, these large differences, what you see here is trying to employ a approximate so-called Lind Hessian that's also used for initializing the geometry optimization. So these are quite bad. You can't really use them. What you also can do, this is a different topic also related to frequencies, is try to derive some properties from that. I'm going through this a bit quicker because I want to get to the next part. So aside from the frequencies, you can try to project the molecular dipole moment of the molecule along these frequencies. So how does the dipole moment change with the molecular vibration that the molecule performs? And with these derivatives together with the frequencies, you can put these together as intensities to a frequency. This gives you an infrared spectrum for molecule. The idea for this project here was, can we combine different methods for frequency calculation and dipole calculation, molecular dipole calculation, with the back thought being, okay, a machine learning interatomic potential in particular nowadays gives you an energy and a force of a molecule. It doesn't give you any additional information that a quantum mechanical calculation would do, like the dipole moment. So can we combine a machine learning interatomic potential for the frequencies with some other dipole moment from a semi-empirical calculation, for example, or an empirical one? We tested this on a benchmark set of 7,000 experimental IR spectra and compared the experiment versus DFT versus these low-cost combinations here. Computationally cost-wise, the machine learning interatomic potentials are, so on the bottom here, you have the system size versus the wall time in a logarithmic scale. Semi-empirical methods is this graph here, these two, GFN 1 and 2 XDB. These three here are the machine learning interatomic potentials, and on the bottom here, these are force fields. And you already see, okay, semi-empirical methods for up to 200 atoms, which is most of relevant chemistry, are still much cheaper than the machine learning force fields and machine learning interatomic potentials. But are they also better? And the answer to that is probably no. Really quickly, how we did the comparison, we are basically looking at the spectrum as a vector and then doing a Cauchy-Schwarz inequality of the reference spectrum versus the calculated one. I have to be a bit careful with this because you can get false positives if you compare different molecules. So it gives you still similar high scores here. But for this benchmark set in particular, we are, of course, only comparing the true structure versus the calculated one for the same molecule. So this is not an issue we have to deal with. Qualitatively, it looks kind of like this. So a value of 90%, 95% is basically spot on for IR spectra. You have a bit more variation if you have noise. So in blue here, this is from the experimental spectrum. This influences this correspondence quite heavily. And if you have larger differences, especially in frequencies, you get lower and lower values, of course. Well, 75% still matches in the peak positions for the most important or the high intensity shifts, frequencies, signals. But in the fingerprint region, you get more variation. And what came out of this study is basically this plot, where on the top we have different methods used for calculating the dipole derivatives. And on the left, we have the different methods used for frequency calculations. These Mason models are the different machine learning interatomic potentials, XTB methods here on top, and DFNFF as the proxy force field. And you can see here, the different machine learning models do outperform the semi-empirical methods at the cost of higher computation time, of course. And it seems to be a valid assumption that we can combine the dipole moment from another calculation than the frequencies coming from the first one. The best value that we got here was for a combination of a machine learning potentials to predict only dipole moments of the molecule with the different machine learning potentials for energies and forces. To give you a relation, so this is a comparison to the experiment, a DFT method like B3lib would have a value of 0.9. So it's already quite close to the DFT values here. Right, with that, I'm coming briefly to the last part of my research. So this is more of an outlook where my research is going towards to. And here it makes sense to look at what are the bigger projects money is flowing into in academia right now, especially in context of AI technologies, aside from machine learning interatomic potentials, so aside from methods to describe the potential energy surface. And one thing that much money and research effort is flowing into is things like retrosynthesis. So in Toronto, they have a $250 million grant right now for this kind of thing. So lab automation, essentially, you have a product and through simulation, you want to design a retrosynthesis. Can see this as kind of a laboratory assistant. Separate from this, and this is what I'm trying to work towards to and securing funding right now, is a computational laboratory analyst. So this is opposed to the assistant that you have a measurement, a spectrum. You don't know what the measurement is for, and you want through simulation and prediction of these things try to find out what you are seeing in this measurement. Yeah? Imagine, for example, a measurement from a distant astronomical spectrum. So you want to find out what molecules are you seeing at the other end of the universe. Okay. Design of such a procedure is, again, what I'm working towards too. It would, in practice, look something like this. You have data from different data sources. So IR spectra coupled, for example, to gas chromatography and mass data. This enters a black box computational machinery, which in the end gives you a list of likely substituents or components of what you are seeing in the experimental data. Explicitly, what's happening in this black box would be some spectral encoder or decoder technology that gives us a list of reference structures on which we can then perform reference simulations or derive data from databases that we already have access to, and combine these to then, for example, with such a match score metric, prediction most that we are trying to simulate in the procedure. A really simple variant could be then, for example, something like you have a spectrum, you try to decode it not into an entire molecule, but into different functional groups. So try to derive what a chemist is doing anyways. He's looking at the spectrum and tries to identify, okay, there's likely a benzyl in there or a carbonyl or whatever. And this is something that's coming slowly into focus in research. I brought you here a really fresh publication. So this is from January. And what they tried to do here is go from an IR spectra as only data source directly to some molecules. They are employing here a neural network called constructive capturing, or capturing, which comes essentially from image processing. So you have an image and you want to process this into a caption for the figure. So you have a figure of a cat and the caption says, this is a cat, something like that, right? And they are trying to apply the same technology to IR spectrum, where from a spectrum with this one loop here, they are trying to predict a SMILES code, so a 2D representation of the molecule, and at the same time have a text completion neural network that tries to complete the SMILES code step by step. So essentially the same thing ChatGPT does when you're prompting it. And in the end, with a back and forth between these two loss functions and these two networks, come up with a SMILES code that's ideally the molecule you're observing in the spectrum. So, two messages here. The first is it works okay-ish for different functional groups. I guess that makes sense. Different functional groups have very specific signals in an IR spectrum. It doesn't work at all, or almost at all, for trying to predict the entire spectrum. So only 16% of cases they were able to predict the correct molecule. And these are all really tiny molecules, like a benzyl ring with an OH group or something. And even then, this network, so this is the attempt you see here, is not deterministic. So different executions on the same spectrum give you a different answer, different SMILES code. So there's much room for improvement. However, considering that the functional groups work okay, this is certainly a technology that could be adapted in combination with quantum mechanical simulations to derive from a candidate list better quality spectra to match to the experiment. The question here is, can we do better with quantum mechanical simulations? And in fact, we can. We showed that in 2021 already. And I apologize for this figure. Despite being on the paper, I had no hand in this figure creation. It's a bit cluttered, but I'm walking you through it. So same question here. We have a spectrum at the beginning and want to predict what is in it. For this purpose, we had a test set of randomly chosen 260-ish spectra from the NIST database, together with gas chromatography and mass measurements. So we approximately knew how heavy the molecule was that we observe here. Based on that weight, we made a candidate list for each spectrum, on average 2,000 different molecules in our candidate list. These are derived from a database, a SMILES code that has to be converted into a 3D structure, so we can treat it with a quantum mechanical simulation. Here, then, you have the option either going for a cheap theoretical method, so directly calculating the IR spectra with something like GFN XTB and comparing it to the experiment, or you're going the more elaborate route, make a conformational screening with GFN XTB, sort out structures that are really far off already from your measurement, to refine your candidate list, and only for this refined candidate list then do a DFT prediction of the same spectrum, and with that do the comparison to the experiment. Question is now, does it work? Does it work better than the machine learning potential with these mild things? And in fact, it does. So on the left side, this is not really important. The important part is here on the right side. If you already terminate at the GFN XTB step, you are already at this 15% of correct predictions, opposed to the 16% with the machine learning network, which increases in top K value. So the correct prediction with GFN2 only, without conformational sampling, going up to 45% in the top 20. So this is already quite good considering the cheap computational cost. If you exercise through the whole workflow, conformational sampling, go to DFT, these numbers rapidly increase. So you have 45% correct predictions of the lowest structure. That increases in the top 20, top K20 up to almost 80% correct predictions. Considering that this study was done with the state of the art in 2021, this is quite impressive. I'm convinced that combining machine learning approaches with this kind of technology, we can do better nowadays. And this is, in fact, where I'm going with my research. Yeah, I'm almost at the end. So possible application for this would be, for example, analysis of polymer decomposition products. What you see here is a pyrolysis machine that's standing at KIT, in fact, so right around the corner. You have an unknown polymer mixture that goes into it that is decomposed in this reactor without oxygen. And you're collecting the coal, basically, that comes out of it, and liquid and gaseous products, where you then could attempt analyzing this with a digital infrastructure. Other applications, aside from the polymer mixture, would be, for example, varnishes or cultural heritage research, varnishes or paints, or trying to go to microplastic analysis, trying to find out what the microplastic plastics are that we are breathing in every day. Right, with that final conclusion, so if we are looking back at this historical development of different methods, assuming the a posteriorists are basically interpretability of chemical data, while the ab initioists are accuracy, so high quality quantum mechanical calculations, then what we are certainly working on right now in this decade is the efficiency aspect. However, all three of these things need to be combined. And the revised citation, so this revision was made by Frank Neese and not by me, would be give us insight and numbers and error bars. With that, I'm really at the end. I thank you all for your attention. A quick shout out to the people I mentioned in my talk. So Tobias, who I did the RMSD pip package with, Lucas, my PhD student, and Andreas for hosting me in Heidelberg, giving me an office and so on. Again, thank you for your attention.